Is it visible presentation? Design of condenser example, is it visible?
No, ma'am.
Hello? Huh?
Now it is. I
It's
think
not?
network is a bit slow.
So what you are able to see?
Design of condenser, and in the red box there is example.
Example. Right. And it is in the PPT mode, huh? Nothing like it's blank rest of the slide.
Sure.
Yes, are you able to see the PPT mode slide?
Yes, ma'am. Now it is.
Okay. So let's start. Good morning to you all. Uh, we are here to discuss the design of condenser, which as far as theory is concerned, that I have already discussed yesterday, where the different like different types of shell and tube condensers and in which condition which should be chosen, that we have discussed. And we further discussed the design of this condenser. And as far as design is concerned, it is similar to shell and tube heat exchanger, except the heat transfer coefficient computation uh, wherever the condensation is occurring, either shell side or tube side, okay, horizontal or vertical, whatever. So that we have discussed. And apart from this, we have discussed how to see the temperature difference average value, and the because when condenser is considered, we have a little bit desuperheating and subcooling, which is as per the requirement of the process. Okay, so how to count all these factors that we have discussed in the last class. Now in today class, I will I will consider one example to show you how the condenser design will be processed, and then we will proceed further. Okay, so first of all, we will have this condenser design example, and the example is like we need to find out overall coefficient for horizontal condenser for the following duty. So it is already mentioned which orientation it is. So horizontal condenser we are given, and if it is not given somewhere, if you are finding the duty is large, or let's say like it is more, I'll tell you the value. Okay, so in that case you can consider horizontal or vertical. Okay, so here horizontal condenser is already mentioned, so we will consider that. Now problem is like that 60,000 kg per hour of mixed hydrocarbon vapors. So if you see the carbon, the vapor has the different components. Okay, mixed hydrocarbon vapor is there, and which is to be condensed in shell side. Okay, so here it is already mentioned that shell side condensation you need to consider in horizontal condenser. So related correlation you can use over here to find out the heat transfer coefficient of condensation side. Okay. Other side, the heat transfer coefficient calculation will be same as we have discussed in shell and tube heat exchanger. Okay. So this is the vapor of mixture of different components, and uh, this vapor enters the condenser that is in shell side at 60 degree, and condensation will be completed uh, completed at 45 degrees Celsius. So what is the meaning of that? That when I'm having different components available in the mixture, uh, each component has different dew point, and so each component will condense at different temperature. Therefore, you observe variation in temperature. Okay, that also we have discussed in the last class. And if it is pure component, pure vapor, then it is only one value. The condensation will occur, will be occurring at. Okay, so in that way you can consider this variation in temperature in shell side. Enthalpies of vapor and condensate are this and this respectively. So basically when we consider enthalpy of vapor and enthalpy of condensate, okay, the difference of these two will be the total latent heat which has been transferred to which has been taken, not transfer, or transferred to another fluid or taken by another fluid. Okay, another fluid over here is water. Okay, so water is available from 30 to 40 degrees Celsius. Dimensions, tube specifications are given. Like we have 20 mm OD, 16.8 mm ID, 5 meter length. So all these values are already given. Vapors are totally condensed. So we the design considering total condensation, and that too we have considered in um, and like yesterday class. Okay, so that is for total condensation. Assume we have one shell and two tube pass with the split ring exchanger. So 1 2 shell and tube exchanger is there. uh, Triangular pitch, we are considering fouling coefficients are 5,000 for each side, because we need to find out overall heat transfer coefficient. So you need to get the fouling factor, and thermal conductivity of wall, it is given like this. So we need to consider the overall coefficient assumed value as 700 degrees Celsius, and repeat the computation until you will find within plus minus 30% range. Yes, yes, yes. Class चल रही है, हाँ। करूंगी। हाँ हाँ. So here we have this uh, plus minus 30% value, what we can say, the variation in overall heat transfer coefficient is acceptable. So let's proceed further. Apart from this, we need some data also, like properties of vapor. So it is given density and viscosity of vapor like this. Viscosity of water you can consider like this. 0.6 density of water, and condensate viscosity 0.16. It is given, and density of condensate it is also given, and thermal conductivity of condensate it is given. We need to calculate pressure drop for both for both for a condenser on shell side as well as tube side using Kern's method. Okay. So here we need to do two things. First is we need to calculate overall heat transfer coefficient, and second is to find out pressure drop. Okay. So we will start with heat transfer coefficient calculation, and as you aware that the first step is to find out heat duty. Okay, and that is basically for not only shell and tube heat exchanger, for any type of heat transfer unit, the first step is to find out heat duty. For that, whatever properties will be required, that we can collect. Okay, so heat transferred from vapor, we are having 60,000 kg per hour of vapor, which is being condensed in shell side, and which is horizontally placed, right? So here I'm having this uh, what we can say, this flow rate of vapor, and it is basically enthalpy of vapor minus enthalpy of liquid, that is condensate. Okay, so difference of this would be the total heat, which is total latent heat, which should be considered. So that we have done. So here you see the total heat duty is around 5825 kilowatt. Okay, so if you see here, this duty is also significant, very high heat duty is there. And because of that, we consider horizontal exchanger. Okay, so I will tell you the limit, like if it is already mentioned in the problem that horizontal condensation condenser will be considered, it is fine. Otherwise, you need to calculate this duty, and beyond that, beyond a certain value that you can consider as the large duty, and then you can consider the horizontal placement. Okay, I will tell you the value. Okay, now here I'm having one fluid is vapor and another fluid is water. So water, you can find out its flow rate, okay, by making energy balance. Okay, and assumed overall heat transfer coefficient we are given as 700 watt per meter square degree Celsius. If it is not given, you need to consider the assumed U value, as we have considered in shell and tube heat exchanger. Remember that graph is there with 3 lines. Okay, so you need to consider that graph. And then we need to find out mean temperature difference. And yesterday we have discussed that if both side, or shell side as well as tube side, if both side variation in temperature is observed, in that case we will consider LMTD for LMTD along with what we can say, FT correction factor. Okay, so LMTD you can find out for counter current, and that is coming as 17.4, and FT correction factor that you can obtain from the graph or from the equation, because 1,2 shell and tube heat exchanger we are given. Okay, so for 1,2 shell and tube you can find out the correction factor, FT correction factor. Okay, and that you can get as 0.92, and considering these two values, you can find out true LMTD or true mean temperature difference, and that is coming as 16 degree. Now, once I'm having this, we need to find out heat transfer area, number of tubes and all, as uh, all these steps are same if you recall the shell and tube heat exchanger. Okay. So area we can find out, it is a simple calculation, no complexity is there. It is 520 around meter square is coming. Area of one tube. Okay, area of one tube, if you see, area of one tube, we are given 20 mm OD. Okay, 20 mm OD, and tube sheet will be available in two sides. So tube sheet thickness we consider in the same way. So at least 25 mm tube sheet thickness should be there. And if it is more than 20 mm, you can, sorry, if OD of the tube is more than 25 mm, you need to consider tube sheet thickness same as OD. Remember? So here I'm having this 25 tube sheet thickness into 2, that we can consider 5 meter length. It is already given. So you can find area of one tube like this. This is basically, if I consider this, this is L effective, right? So number of tubes are coming as around 1672. So we need to consider the value as 1673. Okay, however, it is 1 to pass, so we need to consider even number. So 1674 would be the total number of tubes we should consider, as you can see over here. Okay, and I'm having 2 passes for tube triangular pitch it is given. So K1 and N1, you can take this value, this 1.249 and 2.207, like that you can see. And then you can find out bundle dia as 1084.7. So it's around 1 meter, which is quite high. Okay, it is only the bundle dia. Shell dia will be much more than this. Okay, we need to add the clearance, right? So for that, we are given with the split ring, okay, split ring exchanger. And for that, that graph we have already discussed before, and this clearance is coming as 75. So shell dia would be 1159.7 mm. Okay. So next is to find out L by D ratio, which is coming as 4.311. Okay. Correct L by D ratio should be within 5 to 10. Okay. But here it is coming lesser. But because we are already given the length of fixed value, that is 5 meter, we will consider it as it is. Okay. If you have chosen the length of your own on your own, then you need to bring it to correct length to bring this ratio L by D ratio as 5 as between 5 to 10. Okay, so here 5 meter length we can consider as it is. So considering this, uh, we will proceed further for tube side and shell side heat transfer coefficient. And tube side heat transfer coefficient procedure is same. You need to consider the area per pass, then the velocity, and that velocity you need to check with the what we can say, with the given limits. Okay, so mean temperature difference over here is for water it is 35 degree. Tube cross section area you can consider like 221.67 mm square, and this is the sectional area. Sorry, this is the sectional area. 1672 tubes were there, and you need to divide that by 2, considering number of tubes per pass. So area per pass you can calculate like this. And then I'm having this tube velocity, which is coming as like this, and it is coming as 0.753 meter per second, but it should be 1.5 to 2.5. Okay, because in the tube side water is there, so the correct velocity we need to choose. Okay, and that is between 1.5. So you know already, right? If I'm not having the tube side velocity in the given range, we need to increase the passes. Okay, so instead of 1 2, we will consider 1 4. FT factor will remain as it is. There is no change. But instead of this by 2, we need to consider 1674 by 4. Okay. However, if you consider this uh, if you consider this 1674, and if you find that whether it should be divisible by that you need to consider. Okay, so if you divide this by 4, it will not come as one complete number, that may be decimal value. Okay, that is it is coming as decimal value. However, if you consider instead of 1674, if you consider 1676, it will be the complete number. Okay, so in that way, you will consider the temperature, different temperature, sorry, not temperature, different number of tubes over here. It should be corrected. 1676 should be there. Okay, now you are considering 1 4 passes, so you need to recalculate the bundle diameter and shell diameter as you are getting over here, and L by D ratio. This is the same thing, right? We used to, we are following the same procedure, uh, uh, following the flow chart, which we have shared in challenge tube heat exchanger design. And then you can have this tube velocity as 1.506. So in that case, you need to consider this 1676 number of tubes, and then tube velocity you need to find out. And area per pass, how you will calculate that should be cross section. That should be pi by 4 di square into 1674 by 4, right? So in that way you can calculate, and you will find the velocity, which is 1.506. Okay. Okay. Just 1 minute. So in this case, if you observe this value, right, 1.506, if you are considering, it is just double to that, double to this value. Okay. However, here you need to consider this calculation in a different way, slightly different way. Like here, I'm having 1676 number of tubes, not 1674. Okay. So based on that, you will find out the area per pass, and then you will find out the tube velocity. It will be slightly different than that. It cannot be just double. Okay, so please make the correction over here. So you will find the velocity within the range 1.5 to 2.5 meter per second. Once I'm having this range, we can find out uh, heat transfer coefficient for tube side, which contains water, and for water we have a specific correlation which you can find like this. Okay, 4200 and the other terms. Okay, so considering this heat transfer coefficient, you can get 551.393 watt per meter square degree Celsius. Okay, so in this way you can find out tube side calculation, tube side heat transfer coefficient. Okay, now we will proceed for shell side. Okay, this is just K1 and N1 value. You can now take this value. Okay, for 1/4 pass. So let's start with the shell side heat transfer coefficient. So in that case, which expression you need to use? Okay, you need to choose this particular expression which is given by Nusselt for horizontally placed condenser where condensation is occurring in shell side. Okay, so this expression you need to choose. You cannot calculate with any other correlation than this. Okay, so if you observe this here, I am having different parameters. Like uh, this thermal conductivity of the liquid, it is for the condensate, it is given. All these properties are given except this. This is not TH, this is capital gamma H, which you can see over here. And another parameter we need to find out is NR prime. Okay, so capital gamma H, when we consider, that is WC by L into NT. Okay, so WC weight, that is mass flow of condensate, which is given with like 60,000 kg per hour. So that we have seen before also. And here I'm having 1674. It should be 76, remember? So this NT should be 1676. So whatever correction I'm telling you, just you please recalculate there. And here one important parameter, that L we have taken as 4.95, and L which is given over here is the total length as 5 meter, but whatever part of that tube is available in tube sheet, it will not participate in condensation. Therefore, L we are considering as L effective. Okay, reducing 50 mm from the length, total length. So we can find gamma H as this value. Okay, NR prime, for that you need to calculate NR, and NR would be the number of tube rows in the center, at the center. Okay, this we have discussed very in detail in the last class, so that you can refer. So here I'm having dB by PT prime. Okay, dB you have already calculated considering 1/4 pass. Okay, so that you need to consider over here. PT prime we need to see, and that PT prime is basically the uh, vertical distance between two consecutive rows. For triangular pitch, it should be 0.87 into PT. Okay, that we have also discussed yesterday. So in that way, you can find out NR as 50.78. Okay, now in this case, you need to consider NR as a complete number, because NR is number of tube rows, okay, which cannot be in decimal, as we discussed for NCV and NWV for Bell's method. So NR should be, we should consider NR as 50. Okay, so NR prime should be 2 by 3 into 50. Okay, 50 because we have round off, because we have a specific value of bundle dia. So diameter is fixed. Okay, so we can consider NR as round off, that you can write somewhere. It should be round off. Okay, NR prime, I'm having 2 by 3 into NR, which is coming as 33.33. Okay, so when I'm considering NR, when I'm considering, these are the complete, these are the tube rows, okay, which will actually exist, right? Which is actually existing in the uh, bundle. However, when I'm considering NR prime actually it is only the value which we consider in calculation. NR prime actually it is not existing. Okay, because why I'm considering NR prime, to consider uniformity in the uniformity throughout the bundle. Okay, otherwise middle portion which has more thick layer at the bottom in comparison to when we move toward left or right from the center in the bundle. Okay, so NR prime is only the calculation purpose parameter. That's why NR prime should be considered as it is, not round up or not round off you need to do, right? So in this way, considering all these parameters, we can find out, okay, we can find out value of this HCB, which is coming as 1427.68. Okay, so that is nothing but HO. HI we have already calculated for tube side coefficient, right? So this is the whole expression for overall heat transfer coefficient, considering 5 different terms, and the what we can say, fouling coefficient is same for both the fluids. Okay, and this is the K, W is the thermal conductivity of the material, which is already given. Okay, so once I'm having this, all these values, we can have overall heat transfer coefficient as 720.3. Okay, if I consider the calculation, sorry, if I consider the error in two U naught values, we can find that as it is well below than 30%. So we can proceed for further calculation. Otherwise, you know that you need to replace this you assumed with the calculated value and restart from area calculation and all. Okay, so that you need to consider. So overall heat transfer coefficient, we are getting within the permissible limit. So we will proceed further. And when I'm considering, so when I'm considering pressure drop, it should be calculated for tube side and shell side, uh, both. And this, first of all, will proceed for tube side pressure drop expression. You know already that we have discussed in shell and tube heat exchanger here, Reynolds number. Then you can see JF from here. Okay, from this graph, and then you can calculate pressure drop in the tubes. Okay, so only thing you need to keep in mind that when you are considering this capital L for tubes, okay, capital L for tubes, it should be total length. Capital L should be considered over here as total length for tube side only. So this value is coming as 47.302 kilopascal. And when we consider shell side pressure drop, that you know that for condensation in shell side, baffle spacing should be equal to shell dia. So LB, it should be small l, right? So LB should be equal to DS. Following the Kern's method, you can find out the cross flow area at maximum cross flow area. Okay, Then equivalent diameter we need to calculate considering triangular pitch. So all these we have already discussed in Kern's method. Reynolds number you need to find. Okay. Now one thing you need to keep in mind that shell side we are having the vapor. Okay. So all properties of vapor you need to consider over here, because we are how we consider that as vapor is entering, we need to consider that condition to find out the pressure drop. Okay, so we will consider the vapor properties, uh, and this Reynolds number you can find as 1.099 or 1.1 times 5. Considering this, you can find out JF from here. Okay. And here, another point you need to consider 8.5. 1 somewhere here. Somewhere here it should come. So that in that case, you can consider baffle cut as 25%, but that should be vertical, right? JF you can find out from this graph at 25% baffle cut. Okay, somewhere here it will be there. So value should be 3.5 around into 10 power minus 2. Okay, that you can see over here. And then we can have this pressure drop calculation. The only thing which you need to consider is instead of total length, we should consider effective length. Okay, and the reason is whatever part of the tube is in tube side, it will not create any friction loss in shell side. Okay, but it will create friction in tube side. Therefore, in tube we consider total length, but in shell side pressure drop we consider only effective length. Considering all these values, you can find out pressure drop as 9786.7. And if you recall the last class, wherever I'm having a condensation, there we calculate the pressure drop based on the vapor property, and just half value of that should be considered as total pressure drop of that side. So just you need to consider 50% of the calculated value. So for a so it should be this value 4893.4. So in this way you can find out pressure drop and heat transfer coefficient. So as both pressure drops are limit is not given, but that you can consider it should be less than 1 bar or so. So if this is that is already the case, so we can have the design of condenser in this way. Okay, so only that site where the condensation is occurring you need to worry about, otherwise the procedure is same. Okay, so in this way you can have the condenser design, and here we are completing this particular topic. Just in a couple 2-3 minutes I will start another topic, because we are having sufficient time now. Okay, so just we can start after some time. Just wait for 2-3 minutes. Thank you. So let me share the next topic and then we will start. So I hope this is visible, reboilers and vaporizers. Are you able to see?
Yes, ma'am.
Okay, okay. So after this condenser, we will proceed towards another very important parameters as and another very important equipment, sorry, uh, which is considered in chemical plant wherever you are dealing with the distillation column, okay, and where you need to consider feed as vapor, we need to have this vaporizer. So the next equipment we are having in design is reboilers and vaporizer, okay. So reboilers, you all understand it is a part of distillation column, and vaporizer is a part of chemical plant, and that is used when we need the vapor as a feed. Okay, so in that case, reboiler and vaporizer both I am considering, because as far as design is concerned, it will be like a design of both equipment is equal, is same, not equal, is same, and only the duty will be different. So you can follow the same procedure for vaporizer, but here we will discuss procedure for reboilers. Okay, so that's why I considered the topic jointly over here. So as far as this reboiler are concerned, that you know already, it is a part of distillation column, and usually placed at bottom, where the liquid enters from the bottom to this reboiler, and certain part of the vapor is converted into vapor, okay. And that vapor and that vapor and liquid both enters into the distillation column, uh, and this type of what we can say, loop is there, okay, from loop is there between distillation column bottom part and reboiler, okay. We will discuss the that in detail, how this reboiler will be placed, and what parameter we need to consider for better designing of this, okay. So reboilers are used with distillation columns to vaporize a fraction of bottom product, okay. So bottom product, when I'm considering this, that liquid is available at usually at boiling point, okay. And that liquid enters into the reboiler, and continuous vapor is formed, and that vapor and liquid mixture enters again to distillation column. So the main thing to consider over here, that only a part of feed is converted into vapor every time. That's why it is called reboiler. Okay. However, what it is doing basically, it is only creating the vapor, generating the vapor. Okay. But the reboiler name comes as the feed uh, is being liquid feed is being converted into vapor uh, again and again. That's why it is called reboiler. However, when we consider vaporizer, in which first feed is completely converted into vapor, and whatever vapor is generated, that pass through the required location or required equipment. Okay. So in that way, that is the only difference. Vaporizer have in which feed enters once, and then vapor formation occurs, and that vapor is transferred. However, in reboiler, liquid enters, a part of that liquid is converted into vapor, liquid vapor mixture together enters into the distillation column. Like this loop will be maintained. Okay, so I hope you understand the difference between reboiler and vaporizer. However, the because both are generating the vapor, so only duty will be different. Otherwise, design procedure is same for both. Further, liquid from bottom of the column is partially vaporized in exchanger, which is usually of shell and tube type. So this is again the shell and tube heat exchanger uh, with different phenomena. Different phenomena. What is the phenomena? Like here, if you see, heating medium is in most cases is condensing steam. It means you have what we can say, one fluid is stream, one fluid is steam, and second fluid is liquid, which is already at boiling point, or because it needs to leave the distillation column and enter to reboiler. So in that space, if some heat loss will be there, it may drop by 1 or 2 degree, then it's boiling point when it is reaching to the reboiler. Otherwise, it is mostly at boiling point. So what is the point to consider over here? When the feed is entering as a uh, when as a liquid at boiling point, whenever it will take the heat, it will start the vapor formation starts immediately, right? So in this case, both the side, like shell side or tube side, whatever you are considering, both the side we have phase change. Okay, if sensible heat will be there, it will be very less, right? Otherwise, in both the side, we have phase change, and that because of that, you need to consider the design in different way. Okay, what is the difference and how we need to consider that? All we will discuss in this topic, reboiler design, right? Uh, So further, boiling takes place either in tubes or in shell, depending on the type of reboiler. So type of reboiler we will discuss, and that vapor formation may occur in tube side or shell side, both way. Okay. So the exchanger that supply vapor to other unit operations are referred to as vaporizer, but are similar in most respects to reboilers. So therefore, design procedure we will see only for reboilers. Further, if thermal analysis, when we consider for distillation column, that is much more complicated in comparison to single phase, because here both side have phase change. Okay. Condenser, in the condenser we usually have one side of phase change. Otherwise, here you will have both side the phase change. Okay. So that is quite complicated to understand. Further, the physical properties of liquid and vapor fractions can exhibit large variation throughout the reboiler, because distillation bottom liquid are usually mixtures having substantial boiling ranges. So therefore, you need to consider, if variation in temperature you observe, you need to consider the mean temperature at which you will see the properties. Okay. So that is some points about the reboiler. Now we will see the types of reboilers. So usually reboilers are of three type. One is the kettle reboiler, okay, or kettle type. Okay. Second is natural circulation or thermosiphon reboiler. Okay, that we call. And thirdly, we have the forced circulation reboiler. Okay, so we will see the details of each of these type one by one, and then we will proceed for design of reboiler. And in this particular course, we will consider design of kettle reboiler as well as natural circulation reboiler or thermosiphon reboiler, not for forced circulation. Okay. So in this way, we will proceed. So let's start with the kettle reboiler. So as far as kettle reboiler is concerned, when we consider this kettle reboiler, it is name given as kettle and you understand the functioning of kettle, right? The surface which is available for boiling, okay, it is completely merged with the liquid, right? Like how you are using the kettle, you cannot just on the kettle without pouring water into it, without pouring fluid into it. Okay, otherwise it will be the that what we can say, the heating plate will be damaged. Okay, so when we consider this kettle reboiler, because in this case surface is already merged in the liquid completely. Okay, therefore it is called kettle reboiler, and by this kettle reboiler, its standard is given as this type of shell has given a particular name, and that is TEMA K shell. Okay, TEMA, you understand that we have discussed before also. So TEMA K shell we need to consider, which is a specific type of shell. Okay, if you recall the what we can say shell arrangements we have discussed in constructional details of shell and tube heat exchanger, there I am having E, F, G type, all these type of. In continuation to that, we have TEMA K shell as well. Okay, so this is the kettle reboiler and tube bundle comprised of either U tube or straight tube with pull through floating head. Okay, or internal floating head. Okay, now if you consider this kettle reboiler, here I am having the liquid which is available at bottom of distillation column. Okay, so it enters from here to this reboiler. Okay, and in kettle reboiler, boiling will occur or vapor formation occurs only in this shell side. Okay, if you consider TEMA K shell, this is TEMA K shell. Okay, a more we can have better visualization over here. This is TEMA K shell. Okay, TEMA K means this type of structure. It is called as TEMA K shell. And in this case, liquid enters from the bottom, liquid from distillation column, exits the bottom and then enters to the bottom of the reboiler. Okay, and what will happen over here, if you see this type of arrangement, this is these are usually U tube. Okay, U tube exchangers, and if you are dealing with heating media which has fouling tendency or corrosive nature, then you can use for internal floating head heat exchanger. But in that case, if you see, U tube has only tube sheet at one place. Okay, but one tube will enter twice in this tube sheet. Okay, so one part of the what we can say, one leg of U tube enters into tube sheet and another leg enters here in tube sheet. So each tube will enter twice in tube sheet, but tube sheet will be available only one side. Okay, so in this case, the vapor formation occurs only in shell side. That is mandatory. Okay, boiling will occur only in shell side. Okay, not in tube side. So tube side we have the heating media. In most of the cases it is steam, so that we can use over here. Okay, so tube side is steam, shell side the fluid which we need to consider for vapor generation. Okay, or bottom of the distillation column, whatever way you can understand. Okay, now the point is here different different parts are there. This you have understood. This is tube sheet, this is cover. Okay, nothing new. But the point is, when I'm having this tube bundle, okay, when I'm having this tube bundle, uh, as it is kettle type, this tube bundle will always be merged in the liquid. Okay, if you see here, I'm having the liquid level above this outermost tube in the bundle. Okay, so how it is maintained? This level, it is maintained by this weir. Okay, this is nothing but the baffle type. So here weirs are there, weir is there, only one plate, and the height of this weir would be more than the bundle diameter, right? Because this weir, the purpose of this weir is the to ensure that bundle should be completely merged in the liquid. Okay, so until unless the liquid level will not reach this point, it will not flow, it will not come to this region. Okay, so in that case weir height should be more than the bundle diameter, right? And apart from this, we have another important region over here is this region. Okay. So for kettle type, for or kettle reboiler, the shell diameter is significantly high in comparison to bundle dia. Otherwise, how you proceed? Bundle dia you calculate first, you simply add clearance into that and then you find out the shell dia. But in this case, shell dia calculation is different entirely. That we will discuss. And here I'm having shell dia much more than the tube dia, sorry, than the bundle dia. And the reason being, because here when the liquid comes from the bottom, okay, vapor formation starts because heating media is already in the tube. Vapor formation start, and as vapor forms from start forming from this tube to this tube, it will keep on moving upward. Okay, it passes through the liquid and moves upward. So this space is provided for proper what we can say, disengagement of vapor and liquid. Okay, because vapor, whatever is coming to upward side, it takes liquid droplets also, so that some residence time will be provided over here to separate the vapor from the liquid, and then complete vapor enters into the required space, or here as well, or here as you can see. Okay, so the this kettle reboiler has an added advantage that it generates pure vapor. Okay, and in most of the cases it works as a vaporizer also, because it transfers only vapor to the desired place. Okay, otherwise we will discuss some other reboilers also, where you will see that mixture enters into the distillation column and their separation occurs. But here separation of vapor and liquid occurs in the reboiler itself. Therefore, shell dia is very high in this case. And therefore, this type of reboilers are costlier in comparison to other type. Okay, so that we will see other types. So I hope the kettle reboiler functioning is clear. And when we do this, we need to consider shell dia design in different way in comparison to bundle dia. Another point to consider over here is also very interesting, like uh, in this reboiler, okay, in this region, what happens? Liquid comes from the bottom and moves upward for what we can say, passing through the tubes. Okay, liquid enters at the top, sorry, enters at the bottom and starts moving upward, right? It means there is no say sinusoidal type or side to side movement of the vapor. Okay, as vapor forms, it simply moves upward. Okay, so the point is uh, as it is directly moving upward, it is not creating any hindrance in this. So in this case, we consider the baffle as complete disc. No cut is available in the baffle. Okay, baffles are only provided here to support these what we can say, rings. Okay, however, that baffle does not consider any cut, because whatever feed is there, it is simply moving upward. It's not flowing like sinusoidal through this bundle, or side by side through this bundle. Okay, So movement will always be in upward direction. So we consider baffle, but we do not consider any cut into it. Okay, so simply you can imagine, like as you are considering tube sheet, baffle you are considering in the same line, in the same way. Okay, with of course a smaller thickness, not as compared to tube side, because the purpose is only to hold, not to decide the flow in shell side, right? So in that way, you consider the baffle, and liquid which is fed by gravity from column and enters at the bottom of the shell through one or more nozzles. So from gravity, liquid is entering. So this reboiler will be lesser, at slightly less height in comparison to this distillation column, so that the flow may occur naturally by gravity. So that is about the kettle reboiler. I'm just showing one video to make you understand so that you can see. Okay, so if you see here, I'm having, this is the kettle, okay, K shell, uh, Tima K shell, and this is basically the cover. And here, this line belongs to the steam line, okay, or where heating media line, okay. And here I'm having this connection is for the tube sheet, and tubes are available like this, so you can see. So you can see that the liquid is start filling from the bottom, uh, and this much section is still at the without the liquid, but liquid. Uh, if you see this is the weir. I hope you are getting it. This is the weir, and uh, whenever liquid will come over here, whenever liquid will come over this surface, then it will start coming to this side, that you will see over here, and by then this bundle will be completely dipped into the, or merged into the liquid. So please see, and these you can see the baffles are there, okay, but these baffle does not contain any cut. Okay, so in this way you can consider the reboiler, kettle reboiler functioning, and I hope different parts of it or accessories of it, mm, that these that is clear to you, and because all these we need to consider in designing. Okay, so that is about the kettle reboiler, and I hope the functioning of that, working of that is clear to you. Now we will proceed towards natural circulation or thermosiphon reboilers. Okay, please give me 2 minutes time. I will just start. Just 2 minutes, please. So let's continue. So here, next reboiler we are having is the natural circulation or thermosiphon reboiler. Uh, Natural circulation, if we are considering, that is when liquid is entering in the reboiler without any pump and returns the vapor and liquid, whatever is there, that returns back to the distillation column naturally. Okay, so this we consider as natural circulation or thermosiphon, and how it looks like and what is the working of that, what are the design consideration, all that we will discuss. So this is vertical exchangers with vaporization in tube or horizontal exchanger with vaporization in shell. So that is very important parameter. If you consider reboiler, kettle type reboiler, there vaporization will always occur in shell side. Okay, it's not like any variation is there, because placement will always be horizontal. I'm talking about kettle reboiler, right? Or placement is always horizontal, and pressure, sorry, and boiling will occur or vapor formation will occur only in shell side. That is the thing. If I consider natural circulation reboiler, if I'm having horizontal type, okay, in this case, both are possible, horizontal placement, vertical placement. If I'm considering horizontal placement, then whatever vaporization is occurring, it will always be in shell side. Okay, because you can understand that we are not using any pump or any media to flow to have the flow in this uh, system. It will occur naturally, so it will be one thing is that reboiler will be slightly lower than the positioning of distillation column, because feed enters naturally by gravity. Okay, and then vapor formation, when it starts, it will always be in shell side, because there we have less friction. Okay, or we can say the friction loss will be lesser in that case. And uh, when the fluid will be in shell side, it means it has to pass through less length in comparison to when it is coming when it enters into the tube side, because in tube side they need to follow complete like flow, and then it will enter into the distillation column. So here we don't consider tube side vaporization or boiling when horizontal placement of exchangers are considered. In the similar line, when I'm having vertical placement of exchanger, vertical placement of reboiler, the vaporization will always occur in tube side. Okay, because this is the least hindering path. Okay, the path which has least hindrance. Vapor enters from the shell and then passing the tubes and tube bundle, and then it exits. Similarly, when the feed enters in the vertical reboiler, okay, from the bottom, it simply enters into the tubes and move upward. Okay, however, if it will enter in shell side, it has to move like this and then exit from here, and then it will enter from here. However, when I'm having this tube side for vertical placement, the looping will be very easy in comparison to other side vaporization. I hope you are getting. So please keep in mind vertical reboiler with tube side vaporization, horizontal reboiler with shell side uh, vaporization, and therefore kettle reboiler also falls in this category, because it will be placed always horizontally. Okay, therefore the uh, vaporization is occurring only always in shell side. I hope you are getting this. So liquid circulation through the exchanger is maintained by difference in density between two phase mixture of vapor and liquid in the exchanger, and single liquid in the base. So let me discuss through this, because phenomena that working is same, but I'm saying that when the feed enters into the reboiler, it will be pure liquid, single phase, right? The thing is, it will be at boiling condition, boiling temperature, but the nature of the fluid is single. It will be complete liquid. Phase is single, okay, complete liquid. And as it moves upward through this tube, vapor will start forming. Okay, so when I'm considering feed at this particular section and feed at this particular section, the phase will be different. Here phase will be complete liquid, and here phase will be mixture of vapor and liquid. Okay, because both moves together. Okay, and as the movement occurs in this, the vapor formation will start, but that vapor and liquid, that also move together towards upward. And when it exits from this side, from the tube, it enters into the distillation column. And at this time, again, the mixture of vapor and liquid enters into this. So final, the separation will occur in distillation column. In this case, no vapor liquid separation is space is provided, as we have the advantage in kettle reboiler. In this case, mixture enters into the distillation column and there separation occurs, vapor moves up, liquid will be assembled over here. Sorry, like this. Okay, so the different move, that circulation is natural, because when here feed enters, it is the pure liquid. Okay, so density would be higher. As vapor formation will occur and the fraction of vapor occur in the mixture density will keep on reducing, and that because of that reduction, the natural movement would be upward, right? So in that case, we can have this circulation, and because it moves without any pump, only with the natural mean it moves, therefore it is called natural circulation or thermosiphon reboilers. Okay, because here we have the change in what we can say, the change in properties. Okay, therefore we have this uh, siphon type of movement is there. Okay, so in that case, to maintain this natural circulation for vertical, it is mandatory that the upper tube sheet, okay, upper tube sheet is this. Okay, upper tube sheet will be in correspondence to the liquid level. So this level as well as this level, both will be equal. Okay, so we will consider the pressure drop of in this tube. Okay, and that pressure drop will be compared with the pressure drop available over here. So this pressure drop would be higher than the pressure drop available in this tube. Then only natural circulation is possible. Okay, therefore it is mandatory that upper tube sheet should be aligned with the liquid level in the distillation column. Thank you. So in this way, you can consider the placement and assembly. However, when I'm considering horizontal placement, it should be well below than the distillation column level. Okay. However, vertical will have the sufficient what we can say level difference, because it is placed vertically. Okay. So in this way, we considered thermosiphon reboiler. A disengagement vessel will be needed if this type of reboiler are used as vaporizer. So in this case, instead of entering into the distillation column, it will enter into another chamber, which is basically the separation of vapor and liquid chamber, we call at separator. Okay. So in that way, we what we can say, we separate the vapors, and then those vapor enters into the required equipment. Okay, or required place, like this. So this is natural circulation or thermosiphon reboiler. Next I'm having is forced circulation reboiler. I think you can understand that very well. We need some media to flow, to maintain the flow of the liquid. Or in other word, we let the liquid enter into the reboiler from distillation column. It does not enter automatically. Okay. So in this forced flow reboiler system, the circulation is driven by pump rather than by gravity. Boiling liquid usually flows in the tube and reboiler may be oriented horizontally or vertically. So in this case, you can say that it may enter into shell side. Just a moment, sorry. अच्छा ठीक है, मैं देख Right. So, in this case, we can have boiling in both the side and orientation may be horizontal or vertical. Okay. Uh, Actually, boiling will be in tube side and placement will be horizontal or vertical because it has pump. So pump will be able to maintain the frictional losses, and therefore a tube side boiling will occur in this case, but placement will be horizontal or vertical in both way. Okay. In this case, both are horizontal, but that can be done. Okay. And these pumps, you can see these are used for movement of the liquid. So when we consider this forced circulation reboiler, this is used where natural circulation is not possible, and where natural circulation will not possible, where I'm having like more viscous fluid, okay, fluid having higher fouling tendency. So all these will be handled by forced circulation reboiler. Okay. Now, we have already seen different, all three type of reboiler, their working and all. So we will proceed for design of reboilers. We will start with the design of kettle reboiler. Okay. So if you consider the kettle reboiler, the cross-sectional view will look like this, and side view will look like this. Okay, this image we have already explained. Now we consider this image cross-sectional view, and if you see, bundle is very small in comparison to shell. Okay, shell die is this much. Just a moment, sorry. No. Okay. Ah. So, if you see in this case, bundle diameter is very less in comparison to shell. And if you consider this dash line, okay, this dotted line, this is basically overflow level. Overflow level means this is from here to here. This is the height of weir. Okay, as you can see over here. Okay, so this is the weir, and weir ensures that complete bundle should be merged in the liquid always. Okay, and uh, as liquid enters into this from bottom, it come in contact with the heating media flowing in a tube, flowing inside the tubes, and whatever vapor will be there, uh, whatever liquid in shell side is available, it will that vapor formation will start from this surface only till the top, uh, what we can say, tube. Okay, so as vapor will start moving from bottom, it what we can say, it passes through the liquid pool and the tubes. Okay, and you understand that when we calculate the equivalent diameter for shell side for this type of for the bundle, uh, the shell side equivalent dia would be lesser than the ID of the bundle. ID of the tube. I hope you are getting. It means less space is available in shell side in comparison to tube side. So what happens when vapor, which when the vapor which are generated at the bottom, they start moving upward. Okay, and as they start moving upward, the it can join other bubbles, other that droplets of vapor. Okay, or other, what we can say, vapor. Okay, vapor ball. And after joining these that vapor, they make a bigger bubble in comparison to the which they have uh, made they are made initially. Okay, so they will size of those bubbles will start increasing when the bubbles join each other. Okay, and because the space in shell side is small, they can completely cover the whole space available between the tubes. Are you getting my point? So in that case, it will work as a blanket. Okay, the bubble will be so large that it covers the this like equivalent dia uh, in the shell side. Okay, so in that way, when larger bubbles are there, it covers the space between the tubes. And when another bubble or another liquid is coming from the bottom, it breaks that blanket is broken, and then the vapor moves upward. So what I'm trying to emphasize here, like whatever mechanism is occurring, that is quite complicated. Okay, and secondly, because this wear ensures the liquid or the bundle should be completely merged with the liquid. The boiling, when we are considering over here, that is like pool boiling. Okay, you must have heard about different types of boiling. So here we need to consider pool boiling, and then accordingly we can have the heat transfer coefficient expressions. So when we consider this kettle reboiler, the steps are similar than the shell and tube heat exchanger, but we need to consider some of the factors in different way. Okay, so what is that difference, how we need to consider, and all these that we will see in design part. So I hope the geometry is clear to you. Another point I would like to mention that this is the bundle diameter. Okay, and this is the wear height. Okay, so this section will be what we can say will be the feed section or vapor formation section. And here when vapor exiting, okay, this space is called as dome segment. Okay, this particular section or this particular section is called as dome segment. And the vapor which is exiting from here, it takes the liquid droplets with it, and then entrained basically the liquid droplet. And then here this space is provided to have vapor separation, then the mixture, so complete vapor is exiting out. Okay, and liquid will remain there. So when you observe in actual sense, there are some froth formation at this rear surface. Okay, and that is because of the mixture of vapor as well as liquid droplets. So in this way, I hope you understand the geometry and how to, what are the parameters which we need to consider in kettle reboiler design. Okay, so let's start the design procedure for kettle reboiler. The first one is defined duty, as always. As always. So how much vapor you need to produce into latent heat of vaporization, that you need to consider. So once you are doing this, you can simply calculate heat duty as m into lambda, right? M would be the vapor formation. Okay, so initially we need to define duty. The fluid placement, boiling should be placed in shell side, and heating fluid should be in tube side, so that you don't need to bother about allocation. What boiling fluid will always occur in shell side, and condensing fluid will be in tube side always. Okay, so that is one job has already been done. Just 1 minute, please. So once I'm having heat duty and placement, we can proceed for a mean temperature difference calculation. And in this, we have three different category. Number one is like because in both the side only phase change is occurring. Okay, so if I'm having a pure component in both side, let's say in tube side I'm having steam as a heating media. Okay, and which we need to vaporize is only one liquid. Okay, which we need to vaporize. So the point is at both side it is the isothermal condition, right? So in this way, difference of these two will be the mean temperature difference. No need to calculate LMTD, that it won't come. Okay, it won't be feasible. So in that case, difference of these two will be the mean temperature difference. Secondly, when I'm having steam as a heating media, and whatever liquid we need to vaporize, it contains different components. Okay, so because each component has different boiling point, so the vaporization or vapor formation will occur at different temperatures. So you may observe variation in a shell side. Okay, tube side will be same. So if this is the case, you need to consider LMTD. Okay. However, if you are having temperature variation at both the side, let's say if you are dealing with mixture of mixture to supply the heat as a heating media, and mixture is there which you need to boil, in that case we need to consider LMTD with FT correction factor. Okay, so in that way you can understand that we have how to choose mean, how to calculate mean temperature difference in different cases. So we will now assume the overall heat transfer coefficient in the similar line as we did for shell and tube heat exchanger. Okay, so once I'm having that overall heat transfer coefficient, we can find out area, total heat transfer area, and number of tubes. Okay, so mostly in a reboiler, the kettle reboiler, we consider the U tube as a tubes. Okay. Usually we consider U tube because we provide steam which is considered as cleaner fluid. Okay, so we can use the U tube. There is no problem. If fluid has fouling tendency or let's say corrosive nature, then we should consider internal floating head. Okay, not this U tube. Okay, so what will happen? Area you can calculate, that nothing new, like Q by U, which you have assumed delta T mean, that you have already calculated. So once I'm having the heat transfer area, we can find out number of tubes. Now in this case, total area, whatever we have calculated, this is same pi d naught and L. And L should be L effective. Okay. If you are considering U tube, right? If you are considering U tube, like YouTube is like this. Okay. So the length of YouTube will be this much. Length of the YouTube would be this much. So length of the YouTube, whatever I have drawn, this is the total length of the YouTube. So if, because tube sheet is available only at this point, okay, and one YouTube will enter twice in this tube sheet. So L effective would be total L minus twice of tube sheet thickness. Okay, because this is considered as one YouTube. Okay, now if in the problem it is given like half leg or one leg of the YouTube, Okay, one leg of the U-tube, then you will consider that length minus uh, tube sheet thickness once only. Okay, so that you should keep in mind, and then you consider L effective, and then you can find out number of tubes. So if you are considering total length minus twice of tube sheet thickness, it means whatever value you are getting over here, that is number of tubes. Okay, however, if you consider the number of holes in the tube sheet, that will be twice of that. Number of holes would be twice of that. However, if you are considering only one length, half length of the U-tube, deduct tube sheet thickness once only, whatever you will find over here, that would be number of holes. Okay, and just half of that would be number of tubes, U-tubes. I hope you are getting it. So once I'm having this, we can find out number of tubes. We need to decide the passes. So in most of the cases, it is one shell, two tube pass. That is sufficient. So no need to worry about the velocity and all. Whatever one to pass, uh, while considering one to pass, whatever velocity you will have, that you consider as it is. There is no need to bring the velocity in the defined ranges. Okay. And once I'm having this number of tubes, we need to find out actual tube count and bundle diameter, because in this case, bundle diameter you cannot calculate by usual procedure which we used to do earlier, because in this case, this tube pitch vary. Okay, it's not always 1.25 into d naught. Okay, tube pitch varies, so you can calculate bundle diameter in different way, and we will find actual tube count. Actual tube count means this number of tubes you have already calculated. Okay, this is calculated value. Actual tube count will be slightly different. Okay, how you need to do this? Using this table, this is I think table C1 to C7. The complete range is given, which I will share with you, and that is available at the appendix in Kern's Surth book, RW Surth book, right? So in this we have tube count for this inch OD of the tube and 13 by 16 inch square pitch. So pitch will be different. That may be triangular, that may be square. Pitch size will be different, and then tube OD will be different. So you need to choose the tubes in whatever dimension you have chosen. That should be similar, same whatever is referring or assigned to each table. So let's say you have TEMA U is the U tube. Okay, similarly, TEMA P or S, these are internal and external floating heads. Okay, number of passes, if I'm considering two, because usually it is considered two only. And let's say if you are getting maybe you are finding a number of tubes as 160. Okay, this value, if this value is 160, okay, for two passes, you need to choose actual tube count as 180, right? 180 would be actual tube count, and corresponding to this if you see, this is the shell ID. Okay, but this shell ID is for normal heat exchanger. This value will consider to find out bundle diameter. Okay, so 180 would be the number of tubes. 13.25 is the value which we will collect from this. And if you consider this is shell ID, bundle dia will always be lesser than shell ID, right? So shell ID, considering 13.25, bundle diameter would be lesser than this value. So we usually follow one thumb rule that 0.25 inches should be deducted from this value always to find out bundle dia. Okay, because the calculation is different over here, as we have different pitch, and apart from 1.25 into d naught, if it is there, then you can use the same expression. Okay, but it is more it is recommended to use this approach, because you are not aware of the shell ID, you are not aware of the what we can say, the pitch more than 1.25 into D naught. Okay, so it will be like you need to use this data. So 180 would be the number of tubes and 13 would be the bundle dia. Okay, please consider this. Please consider this shell ID is not the shell ID for the kettle. This shell ID for normal heat exchanger when you are having 180 U tubes. Okay, so bundle diameter would be somewhat lesser, and that less value would be whatever value you see from this table, just deduct 0.25 inches from this. Okay, so that should be the bundle dia. And we need to find out heat transfer coefficient. Just quickly, I will cover. Uh, so if you see, this is a very complicated empirical correlation it is given for boiler design to find out heat transfer coefficient. And this is HNB, this is for mixture, this is for single component. Okay, so you need to consider this FM, which is given by this depending upon inlet and outlet temperature of the boiling fluid, and single component HNB, which is you can calculate from this. Okay, so that you can obtain from mixture. Otherwise, you can use this simplified expression where critical pressure must be given. If critical pressure of the liquid of or the feed it is given, then you can use this graph, use this equation. Otherwise, not. Okay. So in this way, you can find out the heat transfer coefficient of what we can say shell side. Tube heat transfer coefficient, how you will find? Because in tube side, condensation of steam is occurring. Okay, if steam you are using or vapor, any other vapor you are using, so that should be condensing in horizontally placed tube side condensation you need to consider. Okay, so you can find out heat transfer coefficient from in that way as you did in condenser, and shell side whatever in this way you can obtain, then you can find out overall heat transfer coefficient. Okay, so in this way, you can find out overall heat transfer coefficient. If it is within plus minus 30%, you can proceed. Otherwise, you need to choose another tube specification. Okay, like that. Okay, so that you can do. Otherwise, you can replace also. There is no problem. You replace assumed value with the calculated value. Okay. So another very important parameter is the critical heat flux. Okay, if you recall the boiling curve. Okay, if you recall, just a few minutes more I will take, otherwise that is done from my side. If, okay, if you consider the boiling curve, it is like this. Okay, here I'm having the flux, and here I'm having the temperature difference. Okay, so driving force basically. So if this is value, if this value we consider, that is nothing but the critical heat flux. It means heat flux, whatever we are considering in that boiling, it whatever heat flux I'm considering in designing, that should be well below than this. Just a moment. Okay, so that would be well below than this critical heat flux. Otherwise, the reason could be that once we increase, once we move beyond the critical heat flux, this we fall in this region where the heat transfer coefficient is quite less. Okay, therefore we need to be less in this part. Okay, so that is critical heat flux you need to calculate for kettle reboiler. It is given by this expression. Okay, all parameters you can see. It's not very much complicated. And the only thing you need to keep in mind, this NT. This NT would be the total number of holes. Okay, if U tube you are considering, this NT should be twice. Okay, so total number of holes is NT. not the total number of tubes. Okay, so whatever Q you obtain, how you will obtain Q in your case, the heat duty by area. Okay, so Q flux, whatever you obtain, that should be uh, that should be less than 70% of this maximum value. Okay, so this you need to calculate 70% of that, this value you need to find, and whatever flux you are dealing with, it should be less than 70% of QCB. I hope it is clear. So in that way, you can proceed for the design of kettle reboiler. Though design is not completed yet, we will continue in next class tomorrow. Okay, so that is the case. That is all from my side. If you have any confusion, you please discuss. We will continue the design of kettle reboiler in next class. Okay. So that's all from my side. So if you have any observation, you please let me know. Okay, if nothing is there, so I should stop the class. Okay, so we will continue in next class. Thank you everyone for your patience.